So, afternoon, everyone. Welcome to the last session of the day. So, my name is Ben Wetenhall. I'm from Newcastle, and I also part of the UKCCSRC as well. And so, this morning we heard from the government and got their perspective. Then we heard industry and the progress that we've made so far. And for our last session, we're going to look at research. And we're going to look at some of the research that UKCCSRC has funded in conjunction with industry as well. Okay, so we'll move straight on. So our first speaker is Peter Clough. He currently works for ERM, but joined them recently. But he's actually going to talk about some of the work he did when he was at Cranfield University. So over to you, Peter. Thanks.
Thank you. Okay, hello. So as Ben said, this work that I'm presenting today was when I was at Cranfield University, but recently, as in the last 4 months or so, I left Cranfield, left academia altogether, and went out to get a real job. So I'm now working for a company called ERM, and I'll tell you a bit about them later. But this work I was doing was something that was really interesting, and Petrofac, who were the co-sponsors for the project, they found it really interesting as well. So we've heard projects at the start, or clusters and lots of other companies around the world, all saying they can use amine scrubbing to capture CO2. That's great. Really well-proven technology. We know how it works. And they're all going to do the same thing. They're all going to use pretty much the same solvent, same material, same process. And there's downsides to that. So one of the downsides is that the amine scrubber, the part that actually captures CO2, some of those amines are emitted out the top of the stack. And so I was developing technology to stop that emission from the top of the stack. And normally, when I have a smaller group, I would say, how do these masks work? But because there's so many of you, I'm not going to embarrass you and just wait here for 10 minutes. So I'm going to tell you. So we've been wearing these masks during COVID for, I don't know, the last 2 years. I don't know how long COVID's been going on for, but they work using a method that you don't really naturally think of. They work using a method called electrostatic precipitation. And you've probably heard that in other process industries where you're trying to capture dust particles from emissions. But it's a really cool technology that you don't really notice in day-to-day life that actually exists in a lot of other places as well. And so what I was trying to do is use that same principle to capture amines from the top of the stack. And there's lots and lots of different mechanisms for how you can capture dust particles or capture particles of aerosols of amines. And the one I was going to focus on was really the electrostatic precipitation, but actually, there's lots of other mechanisms that are taking place at the same time that we need to consider. And one of the other things that was mentioned actually in the VPI talk, they said that the pressure drop at the stack was very small. And that's because you've got a blower that's designed for a certain flow rate and a certain pressure drop. And you're then going to put that into a CO2 capture unit where you're going to drop even more pressure. And then we're now saying we need to add something else onto the back end of that amine capture stack to get rid of something else, but we have got even less pressure drop. So it's a really difficult position to actually try and capture anything. So you've got options. You could use an activated carbon bed or a sorbent bed. You can use a water wash. You already do water wash anyway, and you could do a chemical wash. And again, they do those already, but there's still some amines that come out the top of there. And maybe there's something better. You could have a better CO2 capture system, maybe not based on amines, or we can try something like electrostatic precipitation. And I think that we're going to find this becomes even more relevant when we start building cluster projects. So with an individual plant on its own, considered just on its boundary, you would say, okay, we can meet our emissions limits. And the Environment Agency will say, yes, you tick the box and you can meet that emission limit. But when you start getting lots and lots of plants using the same technology, all emitting small amounts of amines into the atmosphere, you're going to have a localized emission problem. And the Environment Agency will then probably come back to you and say, well, that's naughty. You need to stop that. You need to improve. And so every single one of those plants is then going to have to improve their existing capture tech that they've already spent lots of money on installing. So they need something to bolt onto the back end or to start their design thinking now. So how bad is this? How bad of a problem? So here are the emission limits set by the Environment Agency for amine emissions, monoethylene amines, how they base it, and the nitrous amines, the degradation products of amines. And you can see they're small numbers, and you can compare those to some of the literature data that's out there, and it's quite scary. So at the moment, based on existing plants, on some existing data that you can find, we don't meet those emission limits. Now, yes, you can improve design, you can plan for this, and you can put these things in place, but you're always going to have an issue of the transient states where your plant is ramping up and down, it's not in perfect steady state, and that's where you're going to find these amine issues are going to become bigger. So amine electrostatic precipitation is a technology that's been around for a long time. Wet ESPs, they already exist. You can buy these off the shelf, and we understand how the systems work and how it's going to work, but what we haven't done before is apply it to aerosol emissions. So I was developing this technology at Cranfield, and I've got a very pretty schematic here showing how it kind of works, but you have essentially your flue gas coming in, and that flue gas contains your amines as aerosols, or at least some of them as aerosols, and if you charge those aerosols, they will move towards an opposite charge plate and become collected. And the things that are not charged will just pass straight through. And that's great because you've got a very low pressure drop, you've got high collection efficiency, you know how this technology works. It's an expensive technology because the cost of the system is high capex and you've got a fairly high opex. But again, it's manageable. It's something you can design and you can meet the emission limits. And we did a whole set of modeling of different amines, and we were looking at where is these natural charges, how would the particles actually align within a field. And so we looked at something called dielectrophoresis, where if you put a aerosol into a electric field, it will naturally rotate itself, or the atoms inside the aerosol will naturally rotate to align with the field. And then if you change the size of one of those plates, they will become naturally attracted towards the smaller size because you've got a higher concentration of charge. And we did lots and lots of scary modeling. So we had lots of scary mathematical equations built into a MATLAB model. And we said, okay, yeah, this kind of works. We think we can make it work. And that was funded by UKCCS under the Flexible Funding 1 project, I think in 2020. We were then successful in building the pilot plant, or the demo plant, using the flexible funding from 2022, I think it was. And we did design work at the very start, so we looked at how we're going to mechanically design this thing, how we're going to design the overall process, and we ended up building it, so that's great. And this was built at Cranfield at the back of one of our facilities, and we've got a nice big red cage there to isolate the high voltage system so nobody can go close to it. Really high voltages were the main thing that was dangerous here. A lot of my other previous work was on very high temperature and high pressure hydrogen systems. So having just a low temperature, low pressure system with just some electricity sounded much safer. But we had so many issues, and I want to present these because we don't really see that. Nobody tells you all of the issues you have with research. You see all of the good parts. You see the final product that says, yes, we worked and it was all good. But actually, there were so many things that went wrong with this project, but they were just normal things. They were completely normal things like deliveries coming in late. We had suppliers that gave us a product like a fan, and the fan didn't meet the specification of that it was supposed to. We had issues with nebulizers and with aerosol generators. We had electrical faults. There were lots of issues that were just natural to this kind of research, but we did overcome them. So once we overcame them, we actually got some data out. And what I'm presenting here is two graphs. On the left-hand side, that's the system, that's some data without high voltage. And on the right-hand side, we've got data with the high voltage turned on. There's different cases of different flow rates and different high voltages, different voltage levels, I should say. But the main difference is that if you look at two cases where the only thing difference is 10 kilovolts is applied to the same system, you can achieve pretty much a 10% increase in capture rate. Now, I said at the very start, there's different mechanisms of how aerosols would be captured, which is why you can still capture some of the aerosols using those other filtration mechanisms. But just by applying that 10 kilovolt, I should say, charge, you can then capture 10% more. And I think you could develop this further and get even higher capture rates. We were limited on time, that's really where we were limited. So next steps for the project would have been to do all of these things. However, as I said, I've now left Cranfield and nobody else is continuing this work, and we've actually dismantled the rig. So unfortunately, for me, the research ends there, but hopefully somebody else in the room or somebody else, I know there's others working on similar technology, will take it forwards and develop it for the future. There's definitely industry interest out there. There's definitely industry need, I think, in the future for technologies like this. So hopefully it will keep getting developed. I want to finish by sort of presenting a little bit about ERM because you may not be aware of who we are. So we are the world's largest sustainability consultancy. We have over 8,000 people, and when I was an academic, we cared very much about metrics and how we performed in league tables, and I found out it's very similar in consulting. We also rank very highly in all of the metrics that you can imagine for consulting. Now, my team within ERM was actually joined between two existing companies, Element Energy and E4 Tech, and we became the Sustainable Energy Solutions Department. And we work across all of these sort of technology areas down the bottom here. My work in particular is in hydrogen and CCS, industry decarbonisation. And we provide services to companies and to industry and to organisations and to countries at government level on how to develop strategies, how to develop business models, and understand what's the feasibility of different technologies, different ideas. So if you're interested in that kind of work and looking what's the feasibility of a new thing or a new idea, what's the techno-economics, does it stack up? That's where hopefully we can help. So I just want to say thank you to everyone who helped on the Cranfield research, and in particular Chet from Petrofac. He was very supportive in the project and the technology and the ideas and the initial starting phase back in 2020 or 2021, whenever he started. Without him, it really wouldn't have happened. So thank you. I'll end it there.
So do we have any questions for Peter? Can you introduce yourself as well, please?
Yes. Thank you. Very interesting talk. I'm Nejat Ramoni, and I'm associate professor in chemical engineering at the University of Bradford. It's just the next city. I have a question. The electrostatic is used in cement industry. It's my experience, and there are some examples of the explosion in high voltage here. Yep. There. So, what do you think in this application? 10 kilowatt is very high, isn't it?
So, I believe those previous incidents have happened where you've had essentially metallic particles going into the high voltage, which I don't think will be the same in this situation for CO2 capture. So I think because the composition of the flue gas going into the ESP would be different, I think it should be okay. But again, more work, more feasibility analysis needed.
Any more questions?
Thank you for the talk. Wahid Niyasar from Chemical Engineering, Manchester. Very interesting talk. Have you thought about that? Because the separation, the removal of the aerosol is linked to the separation distance between the particles and the surface and also electric field.
Yep.
The other way around it to improve the efficiency is that to go to the tighter pores, of course, your pressure drop will increase. So have you thought about using porous materials in this way that your pressure drop will increase, but instead you can go lower voltage?
Yeah, we have. We did quite a lot of modeling on different plate designs and distances and what's the effect of those different distances. We looked at what's the effect of surface material and what's the properties of those surfaces. So yeah, we did do a lot of work around that, and we came to a design of that plate system that we thought which should work. And that was really the initial phase. We did submit a patent through Cranfield as well for that initial design, that initial design of the plate system. So yes, we have considered it.
Got time for one more?
Thank you for the presentation. James Yetman, Department for Energy Security and Net Zero. I understand that this is obviously in a very early stage and it's not commercially viable products yet.
Yep.
But what do you think the economic viability of the product is, given the high capex and opex restraints that you mentioned?
So I think I'm I'm probably overstating how expensive it probably is, because the amount of current you're going to be flowing into the system will be quite small, and therefore the actual operating cost is going to be quite small. CapEx is defined by the size of the high voltage generator, essentially, and that is fairly high. I think it should be still feasible for an industry to apply this technology, because they will be looking at a wider scale plant. And if you're looking at it from a brand new build CCS plant, they're already spending billions probably, and this is going to be millions out of that billions.
Okay, I think we'll have to move on there to keep to time, but thank you again, Peter.
Thank you.
Last but not least, we've got Daniel Mullen. So Dan works for SSE and is finishing off his PhD at Edinburgh, but he's going to talk about some work he did while he was seconded at the University of Sheffield.
Yep. How you doing? So yeah, as Ben said, I work for SSE Thermal, and I've been asked to give this presentation today because I had a bit of a weird situation where I was, like Ben said, seconded to Sheffield for 6 months working on this project, and then got hired by SSE. So not necessarily correcting my own work, but close enough to it. So yeah, before I get into it, a bit of PR. SSE Thermal is a energy provider within the UK, one of the biggest energy providers in the UK, and we own and operate thermal generation plants. And we've set ourselves quite challenging goals, or net zero goals. So we are aiming to produce 3 gigawatts of low carbon generation by 2030. We're going to reduce our carbon emissions by over 70%, and have over 0.5 gig of low carbon hydrogen production. And we see ourselves as providing the dispatchable, flexible, low carbon energy that is required to back up renewables and all those good stuff. So we have a presence across almost all of the industrial clusters, from Peterhead up in Scotland. That's going to be hopefully one of the first decarbonised CCGTs in the UK. We have Keadby Power Station. We also have a few hydrogen projects that are going ahead across the UK. So there's Albra, Pathfinder, and storage associated with that. So we're looking at hydrogen storage and then feeding it into a GT for dispatchable power. And yeah, we have quite a few power stations around the UK that we're actively looking at alternative decarbonisation methods for. So with that out of the way, I'm here to talk about PCC Care, which was a UKCCSRC funded project. It was ran by the University of Sheffield. John Gibbons was the PI on it. And it received 50k in funding from the UKCCSRC, 10k from SSE Thermal, and another 10k from Bechtel. So it was an industry supported project. It originally stemmed from another UKCCSRC project that was completed by the University of Sheffield again, looking at modelling ultra high capture rates in post-combustion applications. That then developed into PCC Carer, and then PCC Carer further developed into 3 different projects that I know of. The one I'm involved in is Focus, which has gotten about $500,000 in funding from DESNZ, and is a 3-year project that's progressing at the moment. So PCC Carer has had quite an extensive effect in ongoing research, and has really led to some really cool work. But basically what we are aiming to do in PCC Carer is to demonstrate and understand the physical phenomenon that has been predicted from process modelling that was completed in COCAP, that will allow ultra high CO2 capture levels to be achieved with low or at least equivalent energy inputs to lower capture rates. This is being done by 6 days of testing at the Turk facility, the 1 tonne a day amine capture plant in Sheffield, and we're looking at again achieving those capture levels of over 95%. And this project is actually still ongoing. We've only done 3 days testing so far, and we've delayed the further 3 days testing so that there can be some upgrades done to Turk that will allow more extensive results to be achieved. And also as part of PCC Care, there's the ongoing development of a lab scale reclaiming capacity capability that there's a poster on in the poster session. So if you're interested, I'm not going to talk about it because it's nothing to do with me. But the Turk testing is what I'm going to discuss now. So it's a bit of high capture 101. This is a graph that there's about 15 graphs in my slide. So this is if you like graphs, this is the presentation for you. If you look at a general amine capture plant, in general, if you're looking at we're using an MEA solvent, 35% weight, and we are modeling capture fraction here. As you increase your solvent flow rate into the absorber, this is illustrative purposes. Doesn't matter what the setup is. It's as you increase your liquid to gas ratio, you get more capture, and this is for a lean loading of 0.2 mole per mole. As you increase your capture, in this case, your rich loading, which is an analog for how much energy you're going to have to put in to regenerate that solvent. So as your rich loading goes down, that generally means that you're going to have to put in more energy to achieve that lean loading again. So if we look at a 95% capture rate, you have a certain liquid to gas ratio that gives you a certain rich loading. If we want to look at achieving higher capture rates with the same process setup, we increase the liquid to gas flow rate. That increases your capture rate, decreases, but you get an associated and quite dramatic decrease in your rich loading because your absorbers are having to work a lot harder, and you just don't get that same concentration of CO2 in your solvent at the bottom of it. And that has an associated drop in energy. However, if we change the process parameters, reduce the lean loading down, you get a different curve, same shape, different location. Now, if we look at achieving a higher capture rate, something around the 99%, we get a specific or certain liquid to gas ratio. That gives us a rich loading that is pretty much equal to the rich loading that you got at the lower capture rate. So your energy input as a result of your loading is going to be roughly the same. And this formed the basis of PCC Care. This is the work that was done beforehand. We wanted to look at what's required to achieve those lean loadings and test out this theory in practice. So based on this, we can see that if you want to achieve high capture rates, you're going to have lower lean loadings. Question is, how do you get those lean loadings? If we look very briefly at how solvent is stripped, you take a vessel that's under pressure, you put in rich solvent at the top, some of that flashes off, and the solvent travels down a packed bed column that is contacted with stripping steam that's traveling countercurrent to it up to the top. That releases the CO2. The mostly lean solvent drops into the bottom of a reboiler. You add heat, that generates steam. Steam goes up, solvent comes down, and your lean solvent comes out at the bottom. CO2 and H2 vapor go out the top of the column, and that's your solvent stripped. Most of you might have seen a graph like this in your past, and it's often cited as the reason why you can't get ultra high capture rates in amine combustion plants or amine capture plants, because if you look at the lean loading that's required to get 95% or so capture, you get it's along that flat line, it's 0.2, and you get a pretty low specific reboiler duty. If we look at the lean loading that's required to get very, very high capture rates, that's way up the exponential path of that curve, and you get an extremely high specific reboiler duty. What was found out though is that this graph is almost entirely dependent on the pressure that you regenerate your solvent at. So as you increase your stripper pressure, this graph moves to the left, and you get an ever decreasing energy penalty that's required to get that lean loading, to the point where once you get to this, what we're calling inflection point, the energy input to achieve this, on a specific basis, the energy input required to achieve the two lean loadings is pretty much the same. Basically, if you're on this side of the line, it's bad. If you're on this side of the line, it's good. So the theory is you can achieve low and lean loadings at pretty much the same energy penalty as you would a higher lean loading, so long as you increase the stripper pressure. That comes with some problems. You have to operate at a higher temperature. That has some degradation effects. We're looking at that at a different project. So we wanted to test this idea, looking at different lean loadings, how that resulted in the capture. Energy was a bit of a funny one because we had some issues with the reboiler, but that's what we're going to be looking at in the next part of the test. But we did 3 days testing, and this very messy graph came out. But we broke it up into 9 runs of 9 different process parameters. And I'm showing this messy graph to show one of the key learnings that we found from this project was that actually the plant moves around a lot, and you get a lot of variability in the plant as you're running. So if you look at the blue line, that's your solvent flow rate. It's constantly going up and down, trying to find that set point, and that has an effect on your plant operation. We also found the stripper pressure quite difficult to control, and again it cycles up and down. But I'm just showing this for illustrative purposes. Once we got this data, I got to pretend to be a data scientist for a little while, and I was able to pull out some relevant data from those tests. So again, we looked at these nine runs. If we look at the green line, we can see that we used 2 different CO2 concentrations, 8% and 4%. We had varying solvent flow rate. That led to varying lean loadings in your stripper and pretty high levels of capture. Again, there's a lot of data here. So if we take a more targeted approach at the data that we're looking at, again, we have the 9 runs. We can see that we achieve very, very high capture levels. Again, a bit difficult to properly measure, but we got somewhere of the 97 to 100% capture. What we did find though is that because of the limitation of the plant, that very often we have to use too much liquid in your stripper, and that, although gave you very high capture rates, gave you quite low rich loadings, which is basically what we were saying in the original graphs that I was showing you. So you got the capture, but you got low rich loadings, and in only 2 cases we got the flow rate about right, where we got a high level of capture and we also got a pretty high rich loading. So yeah, quite challenging to operate the plant exactly as we wanted to and within the constraints we wanted to. One of the learnings that came from PCC Carrier was almost by accident. When looking at the data, I thought it'd be interesting to plot the stripper temperature profile, sorry, for all the different runs we got, and we've seen some pretty distinct patterns, wherein we got 3 distinct lines at the top, which were associated with the different stripper pressures we were operating at, and they were all very, very high, and then curved off the bottom. And we had one particular run, the last run, that again just happened by accident, where the temperature profile was completely different. Started off high, went down low. What we found was that in the runs where you have this distinct temperature profile, you had a high energy input. And when you had runs where you had, when we had this more linear decrease in the temperature profile, you got low energy input. So we wanted to understand what was happening there, so we did some modelling, and I'll run through 3 sort of different scenarios. The first one is the important part to look at here is the temperature profile. In green, you can see that you see a temperature profile that was similar to what we've seen in the test data, where it's very flat and then drops off quite dramatically, and you get an associated very high boiler duty of about 4 gigajoules per ton. Important to note that this particular modelling case was for a very low lean loading, so it's 0.09 mole per mole. If we then take the opposite situation, where we have at a high lean loading of 0.15, we see that the temperature profile decreases quite rapidly and just flattens off. And we have a lower boiler duty associated with this, but basically nothing happens for half of your stripper. So you're wasting the majority of the capex that you've already invested. The third case is the Goldilocks one, which was the one we accidentally hit in the test program, where you get the same low reboiler duty, but you're fully utilizing all of your stripper, and you don't get any excess steam coming out the top of the stripper, so you don't get that increase in boiler duty that we're seeing. And yeah, so we modeled all these cases, and you could see it from the model that you get these very distinct temperature profiles from going from A to D. A has a very high lean loading, D has a low lean loading. So as you decrease your lean loading for the same stripper pressure, you get this increase in the temperature profile that eventually leads to an increase in energy input, because what it turns out is happening is that you're rejecting a lot of steam from the top of your stripper. And then John just happened to be talking to some people in NCCC who had data from their operations, and as it turns out, they had data that confirmed exactly what we were predicting. As you've seen, these temperature profiles that follow this exact path, and you get an associated decrease in energy penalty as your temperature profiles move towards the right. The last thing I'm going to talk about today is a sort of an idea that was developed alongside PCC Carer, which is this absorber corner, a so-called absorber corner, where you have a design point that you want to achieve. It's sitting on that corner of the absorber absorber profile as you increase your liquid to gas ratio. So you get a very rapid increase in capture, and then you get a tapering decrease. So you want to work halfway up that. And if you go too far to the right, you get your flow is too high, and you get a high energy penalty because you decrease your rich loading. If you go too far from the to the left, your energy will reduce slightly, but you'll get a sharp drop off in capture. And just to illustrate what I was talking about earlier with the flow variation that we found in the Turk plant when it was operating. So the flow was oscillating, and that leads to operational challenges because you're working within that absorber corner, and you want them to tighten it up. But if you're going towards high capture rates, this becomes even more important, because if you plot down, you can see that the energy required to achieve the same operational parameters it's much more sensitive at high capture rates. You need much more tightly controlled process parameters in order to maintain yourself within that window, because it's less forgiving at high capture rates. So yeah, briefly, PCC Carer was looking at reclaiming as well. Again, like I said, I'm not going to talk too much on this. You can talk to Martin later on if you want, but they're developing a reclaiming rig within the University of Sheffield, and they've got some interesting results on operating a reclaiming system for an MEA solvent. So yeah, that's pretty much me. Some of the key learnings. Basically, your L/G ratio in the absorber can't be too low, or you're not going to get the capture level that you want, or too high, because you're going to get a decrease in your energy efficiency. You need to operate within these very tight margins, and control your input to your absorber within those tight margins. From from a stripper reboiler, achieving low lean loadings perspective. Pressure, it's a critical factor for achieving these low lean loadings at reasonable reasonable energy inputs, because if you don't increase the pressure as you reduce your lean loading, you will get some steam rejection from the top, which is why you get that increase in reboiler duty. And yeah, I'm not going to go through too much of these, but the liquid flow from the stripper can't be any higher than the energy available to get that lean loading, because you won't get it. You won't strip the lean loading required, and then you'll have a richer solvent than you need, and you won't get the capture, and you get a feedback loop that throws everything in a whack. Your rich loading can't be too low, or else you'll get a lower lean loading than you wanted, and you'll pass that inflection point, and you'll get a high energy input. And yeah, that's pretty much it. PCC care is still ongoing. We've another 3 days of testing planned for the middle of the year, after testing on the other project focus finishes. So we're getting a new high temperature heater that's going to allow us to achieve these inflection point operations, and hopefully have some more interesting results to share.
Okay, thanks, Dan. So we've got time for one or two quick questions.
Hi, Mike Gorbanov from Brunel University London. Thank you very much, Daniel, for the presentation. A quick question on the savings effectively on the reboiler duty when going to the high capture rate. Does the increase in pressure that you do, albeit the minimal increase to 1.5 bar in the maximum scenario, do you evaluate that as a whole, as in the savings that you get from the reboiler duty, are they not compensated by the increased pressurization requirements?
No, so not necessarily. So the way that the stripper operates is that you will generate operating at a higher pressure will actually give you a slight energy benefit, because you will have to compress your CO2 less. Where the trade-off does come down to is that operating at these higher pressures increases your operational temperature of your stripper, which means you need a higher temperature steam source to drive that regeneration process, and that then requires high quality steam, which has an increased parasitic draw on your power generation plant. And yes, this is the short answer. We have looked at that, and headline figures is it roughly pays from purely thermodynamic point to get to a lean loading of about 0.05 or 0.06. So it's way lower than we were ever planning on operating at. And then you start to see the economics becoming a bit more challenging, because you get a rapid increase in the parasitic draw from your CCGT.
One more quick one.
Thanks very much. My name is Mayowa from VPI. I think what would be nice to see would be some cost metrics. Just comparing, let's say, the typical design to this optimized concept, which
it just so happens I'm just about to publish a paper on that exactly. So
that's not the question. That's just
okay.
Yeah, that's just more.
There's a paper coming.
Yeah, okay. No, that's cool. Now you touched very briefly on what you consider to be a key, perhaps, of challenge of this concept, which is around regenerating the amine at a higher temperature and potentially the degradation issues that could accompany that. You're looking into that, but I just wanted to understand how far have you gone into trying to understand, because that could be a big issue, right? If you
thanks a million for your question. You hit the nail on the head. That's exactly the big problem with this, and the unanswered question with this process. Again, I've been doing some work with NTNU looking at this question. So they've developed a model for predicting thermal degradation of MEA solvents under different temperature conditions, and we're looking at what the effect on the economics of the capture process is when you include the extra degradation that's predicted to occur from operating at these higher temperatures. It doesn't look to be too bad. I think from a thermal degradation perspective, there seems to be about maybe a 30 to 40% increase in thermal degradation resulting from operating at these higher temperatures, but you're still talking about reasonably small numbers. But I will hasten to add that this is an entirely theoretical model that we are looking to publish at the moment, and we would need long-term testing at these stripper pressures to really quantify how this affects the operation and the degradation associated with it. But I completely agree, it's an unanswered question that we're hoping to answer at some point. But the model predicts that it shouldn't be too bad.
Unfortunately, we're out of time, but can we say thanks to Dan again, please?